Chairman Lobiondo, Ranking Member Larson, and members of the subcommittee. I'm a professor in the Department of Aeronautics and Astronautics at Stanford University, and I'm a third-generation pilot. My research for nearly 10 years has involved statistical estimation of risk and the development of technology for enhancing aviation safety. Personally, I find the rapid acceleration of unmanned aircraft technology to be the most exciting recent development in the field of aeronautics. The proliferation of unmanned aircraft has made aviation accessible and inspired a generation of eager university students in a way that we haven't seen for a long time. I came to Stanford in 2013 and started the Stanford Intelligent Systems Laboratory, or SISL. My graduate students call themselves Sizzlers. I came to Stanford after spending 7 years at MIT Lincoln Laboratory. It was a wonderful place to work, and I got to know a lot of brilliant people. Well, one of the main problems we worked on was aircraft collision avoidance. And this led to the creation of the ACAS-X program. So ACAS-X is an airborne collision avoidance system that tries to avoid collision with a high degree of reliability. And this is hard for a few different reasons. The first reason is we have imperfect sensors. The second reason is it's difficult to predict exactly where aircraft will be in the future. And the third reason is we need to very carefully balance between safety and alert rate. So safety and efficiency. And it turns out these three challenges are present in a wide variety of other autonomous and semi-autonomous systems, ranging from automated vehicles to medical decision-making systems.
And so when he joined, he was like a brand new professor. So I got to see him give his professor talk to everybody. His first thing was aircraft collision avoidance. And we happened to be there at the same time as a lot of the buzz around autonomous driving was really like growing into something large. As I joined, it kind of became a clear opportunity of, hey, we can merge what Michael did with this new phenomenon.
At the time, convolutional neural networks were breaking benchmarks for image recognition, and also DeepMind's algorithms were starting to break benchmarks for video games that humans had set.
When I came to Stanford in 2013, it was around the beginning of the deep learning revolution. It started with the AlexNet neural network that was able to recognize objects in images. And shortly thereafter, DeepMind was able to create a neural network that could play Atari games, a variety of Atari games, from visual input. Google quickly acquired them. And then shortly thereafter, DeepMind was able to solve Go. Back when I was an undergraduate here at Stanford in the early 2000s, I was told that Go was beyond what was achievable. So even though IBM was able to create a system back in the 90s that was able to beat the world expert, Garry Kasparov, in chess, that Go is completely different. It would require a different level of intelligence.
The beginning of my time in SISL, I remember when AI beat AlphaGo, and that was like a really big thing, and everyone was like watching the matches and following along, and I just remember that was a really big development.
It was really, really interesting because for quite a few people in the lab, the same techniques that were being used, but of course at a much larger scale to play AlphaGo, we were literally learning in the lab and using and applying them to either autonomous driving or drones or aircraft, so it was pretty fun.
In SISL, we work on building mathematical models and algorithms for decision-making under uncertainty. Our work spans three different areas. The first area is in modeling. The second area is planning, and the third area is validation. In modeling, what we're trying to do is go from data to probabilistic models of behavior. And this might encompass driver models or pedestrian models or models of aircraft behavior when they come in close proximity. What we want to do is have those models capture the full variability that we see in the real world.
Modeling the environment of self-driving cars requires reasoning over spatial and temporal information and then making multi-futuristic predictions. So from an engineering perspective, we need to choose the right environment representation that captures all the necessary information, suits well with the learning process, and then is robust to sensor failures. To tackle these challenges, we're developing a LiDAR-based occupancy-grid prediction approach. So it's a probabilistic representation of the environment that relies solely on sensor measurements. To demonstrate the effectiveness of our prediction approaches, we are collaborating to integrate it with control frameworks on a vehicle prototype. This will enable the vehicle to successfully avoid moving obstacles.
In my view, the most challenging aspect of modeling the environment, particularly for autonomous agents, is the human aspect. What makes self-driving cars, for example, so difficult is that we have humans in the space. So we have drivers that are human drivers, we have bicyclists, we have pedestrians. All these people on the road is what makes the autonomous system and modeling the environment so challenging. And also the most important part, right? Because we don't really want these systems to operate in isolation from humans. The whole point is that they're supposed to support humans.
I think AI offers a lot of benefits, and I think humans also offer a lot of benefits from a different perspective. My high-level goals of my research involve basically getting the best of both worlds. So how can we combine the decision-making capabilities of humans with machines and overall make a better joint decision in times of uncertainty?
The standard model for representing decision problems is the partially observable Markov decision process, or POMDP. It captures different sources of uncertainty, including state uncertainty due to imperfect sensor information, as well as uncertainty in the outcomes of our actions. And it's very important to be able to capture these sources of uncertainty in order to build robust decision-making systems.
So there are a ton of challenges with uncertainty in autonomous driving. One of the most important is sensing. So if you have rain or snow or fog that's blocking your sensors, how do you still understand what's around you even when that's happening? POMDPs provide a very systematic and flexible framework for combining all of these different uncertainty characteristics and uncertainty considerations into one optimization problem so that we can find the best thing for an autonomous system to do, even in spite of all these sources of uncertainty.
And then using methods like Monte Carlo tree search to do a lot of rollouts which simulates different possible future scenarios depending on whatever other people might do as a reaction to your own planning.
So a standard approach that we use is known as Monte Carlo tree search. And this is the approach that was used for solving Go. And the idea here is to efficiently entertain the possibility of different futures and reasoning at different levels of detail, the space of possibilities, and optimize with respect to them.
Even though we apply our methods in application areas such as autonomous driving or aircraft collision avoidance, these methods are usually general enough to be applied in different applications as well.
POMDPs are super powerful because they can handle a ton of different decision-making problems. If you can formulate your problem as a POMDP, you can use off-the-shelf solvers to solve it.
We use a lot of these same miniaturized sensors that they've developed for autonomous vehicles, for example, to assist people who have blindness or visual impairment to help them navigate. And so we developed a cane that uses a lot of these same sensors and decision-making algorithms to help people go outside the home and be independent and go to a new place that they've never been before. And so in that way we can kind of enable this new technology with those same types of sensors and algorithms.
We've had a number of great collaborations with the medical school. One area that we're working on right now is in optimally transporting stroke patients.
Right now, SISL and our research group are working with 2 doctors of the neurointervention clinic here at Stanford, looking at how we can address the hospital triage problem of when you pick up a patient who might have a stroke, where do we route them to? And this problem handles both the side of uncertainty with what type of condition this patient has and where we should bring them to in order to save time when it comes to delivering them to their treatment site. So SISL and the research that the lab is doing is providing really a framework for how do we model these uncertainties in decision making in a way that addresses the complex nuance of treatment, diagnostic decisions, triage decisions in a new light, which is really exciting.
We live in California and we care a lot about wildfires. It turns out that wildfires behave in a way that's uncertain and can be difficult to predict. And we need to make the best possible decisions in order to save property and lives. We have explored a few different research areas, including the optimal surveillance of wildfires, as well as optimal mitigations for the spread of the fire.
So wildfires are really dangerous for manned aircraft. It's not a good place to fly over. So if you can have an unmanned aircraft do the surveillance or give fire suppressant, that can help reduce the risk to human life. And eventually, if you want to have a whole team, multiple aircraft, it becomes a burden to have somebody manually pilot these aircraft. So giving them that autonomy, ability to kind of navigate themselves and decide where to go for themselves without colliding with each other, can help increase the amount of surveillance or fire suppression that you're able to do.
Another really exciting area, which we are exploring in collaboration with NASA JPL, is subterranean exploration.
So the DARPA Subterranean Challenge was a robotics competition that was meant to push the frontier of field robotics. So the whole focus there was really on simulating those search and rescue scenarios to push the field of field robotics further, to actually be able to create these systems that were ready to be deployed in a search and rescue scenario. So it was a huge team. We were working with JPL was the lead on the team, and then we also were working with folks from MIT, Caltech, Georgia Tech, and then a lot of just other universities all around the world. SISL was focused on the planning part of the autonomy stack. And so in the autonomy stack, we have perception, we have planning, and we have localization. And so we were focused on the sort of decision-making under uncertainty side of how do we plan where the robots want to go, and how do we coordinate that planning amongst multiple robots, whether they're aerial or ground robots.
We have also applied our research to the space industry.
The problem of satellite task planning deals with deciding what a satellite should do throughout its life. Should it image and collect data? Should it downlink that data? Should it recharge, or should it maneuver? Historically, people have done this planning manually. That's what you see when you look at Apollo 13 with people in control rooms, but with lower cost access to space, there are more satellites launched than ever before, and people simply just can't keep up. So we need new systems, algorithms, and software to automate spacecraft operations, so we put the satellites constantly to work, delivering valuable data and insights to people around the planet. The thing that excites me most about this research is how it can be used to help people around the world. I've used it for monitoring illegal deforestation in the Amazon. I've seen it help people catch illegal fishing in the Galapagos. I've watched it be used for disaster response, automatically tasking images of volcano eruptions and getting data to first responders around the world, for seeing where they need to deploy people or assets to help humans around the world recover in a faster way than we've ever really been able to do before.
We have also been collaborating with NASA Ames, actually with a former SISLer, Edward Balaban, on the Viper mission. It's a lunar mission involving a rover. The rover has a variety of different sensors, including radar, a mass spectrometer, and it can drill and take samples and analyze them. It also needs to arrive at a particular location at a particular time in order to open its solar panels and recharge.
Sherpa is an AI system for strategic mission planning, and it's based on formal decision-making under uncertainty. The Viper mission is its first application, and if we're successful, to the best of my knowledge, it'll be the first application of formal decision-making under uncertainty on a space mission.
We have also been collaborating with the School of Sustainability. Sustainability is a major societal challenge, and many of those problems can be framed as POMDPs.
Some decision-making problems that we look at in sustainability are all related to utilization of the Earth's subsurface. So for example, one of the key technologies that's emerging is battery technology. And battery needs certain rare elements that we find underneath the Earth's subsurface, and we need to discover those elements and mine them out for batteries. And so we actually use AI-assisted decision-making to figure out where we should explore on the Earth's subsurface in order to uncover minerals. What makes the sustainability problems a bit more different is that for number one, we have very, very large amounts of uncertainty. So because these reservoir structures are thousands of feet below our feet, we know very little about them, and we can only do a handful of things to sense or observe the state of these reservoirs. So because we have such high uncertainty, we have to rely a lot more on modeling and simulation in order to make good decisions.
A lot of the technologies of our time that we have learned to love, like for example cars, airplanes, medical industry, or even the energy industry, have really been made possible for civilian use through centralized supervision and centralized safety guidelines, as are given, for example, by the FAA, the FDA in the US, or the EASA in Europe. And so today there's been a big push and an emerging technology in the data-driven world. So for example, machine learning, AI in general, yeah. But the adoption of such data-driven technologies is not so easy, especially in safety-critical applications, because we are missing such safety guidelines as have been proposed for other technologies.
I feel like many people have different opinions about autonomy, but it's important as engineers that we have tools to systematically evaluate whether or not these systems are acting as intended.
So AI safety is about ensuring that the algorithms that we develop behave in the way we expect and in a safe manner when deployed in the real world.
So one of the tools that we use is known as formal verification, and that's where we actually build up mathematical proofs about the behavior of our system. So under a set of assumptions, we can actually prove that our system stays safe over long periods of time. Sometimes those techniques actually aren't that scalable to very complex systems like autonomous vehicles, for example. And so in that case, we rely on adversarial sampling. So we actually try to construct challenging scenarios for the autonomous vehicle to uncover the ways in which it might fail. And we use that to inform the design on the next iteration.
Unlike traditional or classical software, where everything is kind of prescriptive code, often just operated as like a line-by-line piece of software, AI systems, which tend to use neural networks, are a lot more complex, and so you can't just look at them kind of line by line. And so this issue kind of becomes, well, over what space do you search for failures, or ensure safety over what domain? And we often call that like the curse of dimensionality.
Major challenges for AI systems include the dimensionality of the input, as well as the combinatorial explosion of edge cases that we see over time.
My work draws on a lot of ideas from statistics and artificial intelligence that really excel in this kind of high-dimensional search that is required of safety analysis of AI systems. So the idea, or the goal, is that a designer or developer of an AI system would be able to use the tools that I'm researching to be able to evaluate, say, the risk or the probability of failure of an AI system during development and before deployment.
One approach that was developed in the lab by Richie Lee is known as adaptive stress testing, and it has been expanded upon by a number of other sizzlers over the years.
Adaptive stress testing formulates the problem of finding the most likely failure path as a sequential decision-making problem. So this makes it so that we can apply very powerful techniques such as reinforcement learning to solve these problems.
So it's actually kind of interesting how you can take a validation problem of finding the most likely failure and turn that into actually a POMDP, which is great because we love POMDPs and we know how to solve them.
I think it's just so interesting that we have this domain where vehicles can't fail. They really can't fail because it's so safety critical. And so I think it's super exciting to be working on these projects where we take baby steps towards a future where these vehicles can make smart decisions and can reason about their environments.
What gets me most excited about SISL's research in AI safety is that if we can continue down this path and we can continue to work on developing algorithms for verifying and validating AI systems or AI techniques, we have the potential to unlock a whole bunch of capabilities for safety critical systems that they didn't have previously.
Of course, my students are very interested in solving difficult engineering problems, but they're also very focused on having a positive impact on society. Naturally, part of this is governance. We have worked with the various regulators to try to come up with policies that ensure the safety of AI systems.
And now for my research, I'm really interested in understanding the industry needs and the industry wants, and also understanding what academia can provide for such safety guidelines, and finally helping regulators understand which type of certification guidelines and safety guidelines would make sense to bring together the different industries.
I'm creating a comprehensive responsible AI assessment where I'm trying to make it super easy for organizations to assess their systems with respect to robustness, fairness, and accountability, and like RAI dimensions more broadly. And then secondly, I'm looking at how we can use AI more specifically to automate AI governance efforts. So anything from, for example, like auditing and monitoring AI systems on a large scale.
SISL has collaborated with a number of different labs across the university, as well as the Human-Centered AI Institute. A few years ago, we also started, in collaboration with a couple other faculty, the Stanford Center for AI Safety. This has allowed us to collaborate with a number of industrial sponsors.
The Stanford Center for AI Safety collaborates with industry partners such as autonomous vehicle manufacturers, autonomous aviation companies, as well as a variety of other companies that deal in high-stakes settings.
SISL has worked with a number of different companies over the years, including Toyota and Allstate. The students work on their theses, they collaborate with them through internships, and in some cases they work for these companies after graduation.
So I've been lucky to collaborate with GE Research and GE Aviation, NASA Ames. I collaborated with OMV, which is an Austrian energy company. I've collaborated with X-Wing, which is an autonomous aircraft startup, and also Cobalt Metals, which is another startup, but they're doing critical mineral exploration.
Michael helped me write a proposal for a research project with Waymo. It was really awesome because I made my own project. I wrote my own research proposal. I had my own collaborators that I brought in, and we then worked with, and a paper came out of that, and that was my final project of my PhD.
The collaborations with industrial partners and the insight that they gave us about the real-world challenges and problems guide the research at SISL and make us ensure that the research that we develop and the techniques that we develop are going to directly benefit the end users of these technologies.
In my research, I've been focusing first and foremost on automotive driving. And I've actually had the awesome chance during internships to actually apply POMDPs to automotive driving and to actually see POMDPs used in real life to handle occlusions.
My work at the intersection of technical AI safety and AI governance more broadly actually has a chance of affecting millions of people. And by just making AI systems more safe and robust and responsible. And that's actually what gets me up every morning.
SISL by default open sources all of our software, including general purpose software as well as software for reproducing our experiments. We want the scientific community to take our ideas and run with them. We have open sourced over 200 different packages on the SISL GitHub as well as the Julia POMDPs organization. One of the first projects of the lab was to create POMDPs.jl for the benefit of the general scientific community.
POMDPs.jl is a package, or really more of an ecosystem in the Julia programming language that pretty much all SISLers have contributed to at one point or another, or used at least.
The main features of POMDPs.jl are the state-of-the-art solvers that we've implemented and a really easy interface for implementing problems that can be formulated as POMDPs. So we want to make it as easy as possible for someone with a POMDP problem. It could be anywhere from ecology to aerospace to geology, to be able to implement their problem well and then to be able to use the best solvers on it as quickly as possible.
I've seen it used GE Aviation, NASA Ames, MIT Lincoln Laboratory, and also a bunch of universities across the world, including the Netherlands, Germany, Austria, and Korea. So it's kind of, because it's open source, a lot of people have access to it, and because, again, we allow you to implement your own solvers or just use things off the shelf, it's kind of been widely adopted as one of the best POMDP packages and ecosystems that's available out there.
Another set of resources that we have made publicly available are our textbooks, including our most recent one, which is Algorithms for Decision Making. We're also working on a new textbook called Algorithms for Validation, and that's being done with a few of my graduate students.
So in terms of general environment and working in the lab, I'd say my favorite thing has been the diversity in all the people. And I mean that in a couple senses of the word. So one, there's like diversity in where people are coming from, both like literally in terms of places around the world and their undergrads and what they were doing before this, but also their expertise and their hobbies. It's like really all over the place what people are really into. But also in their research, and this kind of like manifests itself in people's research, that a lot of people are working on a lot of different things, and that's made it really fun and easy to be able to go like learn something new and try to make a contribution in it.
We want SISL to be a diverse laboratory. We take students from a variety of different disciplines, aeronautics and astronautics, computer science, mechanical engineering, and so forth. The students enter Stanford through a variety of different pathways.
Being a rather big group, we have an extremely diverse environment, like both academically speaking and also culturally speaking, like people from so many different backgrounds. And whenever I have a question about literally anything, there will be someone in SISL who knows at least a bit about it or can point me in the right directions, and that's really great.
The environment at SISL during the early days was collaborative. It sounds counterintuitive for a research lab where everyone's kind of tackling their own project, but I thought it was really collaborative and I really enjoyed working with my peers and I learned a lot from them.
We were very fortunate in the early years of SISL to have a group of students who were very kind and supportive of each other. There was a culture of support, and this led to many very positive experiences, and with that momentum, I think people today would say that SISL is a very supportive and nurturing place.
Coming in, it was like, oh wow, like everybody was interested in what I did, it was very welcoming, and like, hey, how can I help?
In the lab, we have postdocs, PhD students, master's students, undergraduates, and sometimes high school students who intern during the summer.
I think one of the coolest parts of SISL is that we really are family, and I think what makes a family really great is that you have older siblings and younger siblings, and you have like this mentorship ladder. And as maybe like what people would probably consider one of the younger siblings as a master's student, I really have great mentors to look up to, and I feel like the most inclusive part of that is that I can ask any question. There's no dumb questions. And I always feel like even if I'm super lost, I have someone to turn to. And that is just like the best feeling in the world.
My experience getting involved in the lab as an undergraduate has been really positive. I remember being really pleasantly surprised by how supportive everyone was and how welcoming everyone was, even from the first lab meeting when I didn't know anyone.
The general environment in SISL is one that's very supportive and friendly. People are very curious and willing to help each other out with kind of their difficult problems or debug some issue. And all that kind of stems back to Michael as an advisor. He's very generous with his time and really wants to help his students succeed. So he's a big advocate for them and helping them to feel proud of their work and to make progress on their thesis.
The most important and unique thing about Michael and SISL is that he really focuses on making not only great research, but great researchers. So he's developed an atmosphere where we can grow as people and learn to work together to do research instead of just focusing on the research itself alone.
My advising style was heavily influenced by Niels Nielsen. I came into his lab as an undergraduate with no prior research experience in computer science. He was extremely generous and kind to me. I felt like I could trust him. So fundamental to my advising style is establishing trust between myself and my advisees.
And I think there's this key line that Michael always tells me, which is, my happiness is 100% aligned with yours. And I genuinely think that captures who Michael is as an advisor.
Michael has this saying that his objective function is to maximize student happiness. And I remember when I first got to Stanford and I was taking his class and he said that, I was kind of like, yeah, okay, sure. But after getting to work with him, I found out that was actually true. That is truly what he's interested in.
He reminded I and a couple of the researchers on this project the other day of his no struggle policy, where no matter what you are doing here should not be a struggle. You should be doing research that excites you and working with people who excite you.
Honestly, I don't know how he does it. He seems to invent an extra 8 to 12 hours in any given day to make time for everyone, from the students that he's teaching in his classes, to myself working for him as a graduate student, to his family and friends who he spends time with and is incredibly giving for helping everyone around him.
I was struggling with my first research project, and I asked Michael a question over Slack, and he responded back almost immediately, got time for a quick Zoom. And the next thing I knew, I was on a Zoom call with Michael at 9 p.m. at night on a work night, and he was helping me debug my code and talking me through some of the math that I was missing.
I think Michael really has some empathy for combining, everything into one package and helping me be successful all around, not just in the academic side of things.
It's not only like, oh, hey, I'm just going to the day-to-day meeting. It's a actual care of my personal life and my development as a PhD student. I think that's just something that sets Michael apart from most of the other professors and advisors I've interacted with.
You don't even hear Professor Kokendiffer come out of most people's mouths. I think the fact that he insists on being called by his first name just really forms this really inclusive and welcoming environment in his lab, in his lecture halls, whatever it might be. And to me, Michael is a mentor. He's obviously my research advisor, but he's also just a friend. And I know he's going to be there to support me through my highs, but even more importantly, enthusiastically support me through my lows, which is really cool.
Also, I'm friends with his family, and I've gone on multiple trips with Stanford with him and his family, and I've just learned so much from not only him, but all of the experiences I've gotten to have with him.
We try to have a lot of fun in SISL. We have barbecues, Chipotle, we ran the Ragnar relay together, we do kayaking, and every week together we play Frisbee.
We have lots of old-time Frisbee players, lots of new Frisbee players, and everybody has a super great time together in the evening just chucking a Frisbee around after a long day in the lab.
In less than 2 years, I made a lot of memories in SISL, and every Frisbee game every week is actually a highlight of my week.
We got a pretty large group of us my first year, I think, to run a Ragnar, which is a 200-mile relay race. So we've actually done 2, but we all slept in a van and we drove from San Francisco to Napa running the whole way.
So over the span of 2 days, none of us really got any sleep. And I remember at the time thinking it was torture, but I'm glad that we did it.
At the time, you're like, I'm exhausted, this is terrible, but afterwards you look back on it very fondly. And kind of those experiences and moments you have with your teammates here, it's really nice.
Every year we have a big spring barbecue where we celebrate end of quals, end of a school year, lots of paper submissions.
One of my favorite memories of SISL was watching Michael fulfill a 20-year dream of his, which was dancing in the Stanford tree, which just was very playful, and he wasn't embarrassed by dancing around and being silly, and I think that epitomizes SISL in just one moment right there.
The alumni of SISL end up in a number of different places, ranging from academia to industry.
I am most excited about the aspects of using this technology and decision making to develop devices or things to help improve people's lives and allow them to be independent and do the things that they're wanting to do. And I'll be starting as a professor at Harvard to continue this research.
After leaving Stanford, I will be joining Rensselaer Polytechnic Institute as an assistant professor in 2024.
I will join UC Riverside as an tenure-track assistant professor after leaving SISL.
Immediately after graduating from SISL, I was a postdoc at the University of California, Berkeley, and now I have my own lab, which does research similar to SISL in the aerospace department at the University of Colorado Boulder.
Since graduating, I work at SpaceX. I started off my career doing regulatory affairs, so getting our FAA licenses for our launches, and now I work as a flight software engineer.
Jeremy Morton, who's also a SISLer, convinced me to come to Waymo, which is autonomous driving. It's what my thesis was on, and now I work on vulnerable road users.
Since graduating, I have been working as a research scientist at TRI. TRI's mission is thinking about how we can support the elderly with autonomous systems.
Since I graduated from SISL, I've been working at Wing as a flight automation engineer. And Wing is a drone delivery company, and so we want to make sure that the aircraft can fly autonomously to customers and deliver whatever goods that they're wanting to order.
In my introductory courses, we talk about how POMDPs can be used to solve engineering problems. But of course, the students are also thinking about how POMDPs can apply to their own lives. And they use it as a framework for thinking about how they can optimize their own lives. In fact, our lab t-shirt on the back says, "Life is a POMDP."